Well, here's another heat transfer problem where we're taking another block of copper and it has a known initial temperature, and then we're going to put that block of copper into some water, and the water is colder than the copper, so some of the heat is going to go from the copper to the water. We know the mass, initial and final temperature of the water, and we know the initial temperature of the copper, and by knowing the final temperature of the water, we also know the final temperature of the copper. And so what we want to know now is what is the mass of the copper. So just like we always do, let's write down everything that we know. And so for the copper part of it, we don't know we don't know the mass. So let's put a little question mark there. We know that its initial temperature was equal to 65.4 degrees Celsius. The final temperature, although it wasn't explicitly given, we know that it will be 24.2 degrees Celsius. And the reason for that is we're told that the water and the copper reach a thermal equilibrium at 24.2 Celsius. So when we have two things in contact with each other like that, and they reach a thermal equilibrium, it means that their temperature will become the exact same thing. So the copper went from a 65.4 degrees temperature to a 24.2 degree temperature. And that gives me a delta T for the copper of minus 41.2 since it went down. Now for the water, put the water over here. We know that its mass is equal to 95.7 grams. We know that its initial temperature is 22.7. And we know that its final temperature is 24.2, which means that it has a delta T of 1.5 degrees Celsius. Not a very good C. There we go. So we've got all the information that we need to solve this problem here. Now, one thing that we need to realize is that when we relate the heats, we can say that the Q of the copper, or the negative Q of the copper, is going to be equal to the Q of the water. So the heat change, let me put that as a little bit lower case there, so we'll say H2O, there we go. So the heat gained or lost, in this case lost by the copper, must be equal to the heat gained by the water because they reach that thermal equilibrium. So we know that the Q for each of those is equal to M times C times delta T. So we can write out an equation here where we have minus mass of the copper times specific heat of the copper times the delta T of the copper. It's got to be equal to the mass of the water times the specific heat of the water times the change in temperature of the water. And so we know almost all of those things except for the mass of the copper. So we get negative mass of the copper times 0.385 joules per gram degree C times negative 41.2 degrees C. That's got to be equal to 95.7 grams times 4.184 joules per gram degrees C. The specific heat of the water wasn't given here, but it was given on a previous slide. That's something we don't expect you to memorize. And the delta T here is 1.5 degrees C. So when I work out both sides here, I get negative M copper times negative 15.86 joules per gram is equal to 600.6 joules. And when I divide all that out, I get a mass of copper that's equal to 37.9 grams.